and welcome to a presentation for Cambridge University Press on vectors. We're going to look at the three different chapters in the Extension 1 and Extension 2 textbooks that relate to this topic. Hello and welcome to the second of three videos going through the vectors content in the Extension 1 and 2 syllabuses. This is for Cambridge University Press. The first video was all about Chapter 8, which was introducing vectors in 2 dimensions. This is all about Chapter 10 and beginning to look at projectile motion, which is also Extension 1. So this is Chapter 10 in the Extension 1 book. There are only 2 parts to this chapter, the time equations, 10a, and the equation of path, 10b. Basically, the content of 10a, if you've taught projectiles before, there isn't a huge amount that's changed except for a slight difference in the way we present the information, so talking in vectors now. But the same principle of thinking both horizontally and vertically applies. If projectiles is new to you, hopefully you'll still get something out of looking through this. We need to think about the origin and the basis vectors, so in other words, where are we setting as our origin in terms of where the projectile is thrown from. For example, if it's thrown from a particular height, do we set that particular height as the origin, or do we set the ground level as origin? We should always be drawing diagrams to help us with resolving the velocity, and then we are looking at making or coming up with deriving the 6 equations of motion, which are also called the time equations. So in order to understand how this works from a vector's perspective, we need to understand what a vector function is. We haven't met vector functions yet in Chapter 8. So here's a quick example that just explains how that works. So suppose we've got 2 boats P and Q. They're at particular points and we'll be given position vectors for those points. We're also told they're moving with particular velocity, and each of those velocities is given as a vector. So if we draw a quick diagram to explain what's going on, here are my 2 boats P and Q at their particular positions, and the arrows are drawn in scale to represent those velocities, those velocity vectors that are given. So if we were looking at P, remembering it has a starting point of 4i plus 8j, if we go back to here, 4i plus 8j was the starting point, position vector of P. And then we're going to say that its displacement at time t is going to be t times the velocity vector. In other words, we're starting at a particular point, and then for every second we move along, or hour, in this case I think it's given in kilometers per hour, so every hour we go along after t hours, you've moved a particular amount according to the kilometers you've gone per hour. Which means we could write it in this form, and if we were to then separate up the components of the vectors, the I and the j, I've got a particular expression which has a t in it for I and a particular expression that has a t in it for j. I could do the same for q if I wanted, which means I could also find distance between them just by playing around with those vectors. We know that vector pq can be written as little q, position vector of q, take away position vector of p, and I can now write that using just normal algebra as an expression as a function of t. So we can play around with vectors in this form. So I could describe a particular particle's path using a vector function like this. So I could say I've got an r of t, which is a family of vectors, and I could write that as this. So if r of t, sorry, going back to the previous page there, is you take 3 plus t, and that's your I component, and you do 1 minus 2t, and that's your j component. That means for different values of t, I can work out how I would write r of t, and it gives me all these different points. So at time -3, I've got it being at 7j, so starting off here. Then it moves to I plus 5j, then to 2i plus 3j, and so on. Each hour it moves to the next point. So in other words, it's moving in a straight line along here. So that's the idea of vector functions, which means one other thing to note there is that I can equate I components and I can equate j components. So if I know that I've got a particular thing xi plus yj, I can say that x must be 3 plus t and y must be 1 minus 2t. And this, of course, is just parametric equations. We've met these before already in the course. So if I've got two parametric equations, I could eliminate the parameter t, and that then gives me my Cartesian equation. So that in a nutshell is what we're trying to do with this projectile motion in terms of vectors. So looking more to the chapter then, this is a very important box, and they're saying the same thing that I've just said here, that we can give the horizontal and vertical components as x dot, so the speed in the x direction, and y dot, the speed in the y direction. And that means we can basically resolve the velocity vectors, but v, the velocity, would be written as the x component of that, there should be a dot on that x, times I, and the y component times j. So the j component, that's the bit in the y direction, that component of the velocity. Now this is a nice example just to make sure we do totally understand what we mean by that. So if I've got a particular projectile is moving with speed 12 meters per second, and first of all its angle of inclination is 60 degrees. So here is the vector representing that speed. It's length 12, it's of angle 60 degrees, so that means 60 degrees positive to the positive x direction. This is what it looks like, which means I could then find the horizontal component of that and the vertical component of that by resolving. So 12 cos 60 degrees. It was worth actually just pointing out to students that there's a really quick way of doing that, is just to remember that it's 12 cos 60 horizontally and it's 12 sine 60 vertically. And I often think about that, about cos is coming home through the angle and sine is going away from home, away from the angle. If you think, imagine this vector as it can sort of flop down to here, or it can pull away to here. So you can write it that way, and once we've got those two different components, then I can just write the vector with the I and the j. Similarly, if it's at negative 60, so we're just simply going that it is going below the x-axis by 60 degrees, and we just have to remember to put a negative in here. So thinking in terms of projectiles then, we've got a few assumptions. Whenever we're dealing with projectiles, we have a point, we consider a point, that the point is what's moving, so the projectile doesn't have any size. We are not considering air resistance at this point. We only have force, the only force acting on it is constant, it's due to gravity, and most of the time we say it is 9.8. The question would tell you if that was going to be different from 9.8. And so we can have a position vector at time t of that projectile and where it's going. That means we could also have a position vector, or rather a velocity vector, at any time t. So it's going to be related to the position vector, and of course we've just done the chapter, if you do the chapters in order, we've just done chapter 9 where we've looked at the whole relationship between speed, velocity, acceleration, and displacement. So looking at the relationship between those in terms of differentiating and integrating. So here I know, if I'm told that we have something starting, being shot out of a cannon, thrown, whatever it is, with speed u at an angle of theta above the horizontal, then I can put that into vertical and horizontal components, and I could write it as u cos theta I plus u sine theta j. So I know that that is what's happening at time 0. So let's go back to the book for a minute then. So in the book we have this idea that we've got these two main equations that we use every time. And as I say, for those of us who have taught projectiles before in the old course, this is not a new idea, it's just a different way of talking about it and putting it together at the end. But we have the idea that horizontally there is no acceleration happening, it's just moving in the distance speed time way, and vertically we have this one force acting on it of gravity, which means the acceleration is negative g, where g is our 9.8. So taking that idea then, what I'm basically saying is that I could express the acceleration vector at time t, so r double dot, so acceleration at time t, as negative gj. So bearing in mind that there's a hidden naught I in there as well. So naught I take away gj would be my overall acceleration vector, which could also be thought of in the separate components as here, as you've got your x part and your y part. This is a really good example to just go through and make sure we all understand how we're going to find these 6 equations. I've put 6 in inverted commas there because of course we can combine each of these, and we could write, as I just showed you, the acceleration vector as 1, which combines equations 1 and 4. I could write the speed equation as 1, which would combine equations 2 and 5, and I could write the displacement equation as 1 vector, so that's combining equations 3 and 6. But just to go through, let's look at what's going on horizontally. So x double dot is 0, I integrate that, I get x dot is a constant, but I know that when t is 0, x dot is this particular value, which I've got from here, my initial conditions, and so I know that that's the constant. That means that I then rewrite, and to get my second equation here, I have now got that the horizontal component of the speed is that particular constant I just worked out. If I go again then, and integrate again, I'm going to get x is, and then integrating this, I get 20t root 3, and another constant, a different one to the last one. I look at the initial conditions, I substitute in, I find that that particular constant must be 0, and now I can rewrite the horizontal component of that initial speed displacement as this with no constant added. So I've now got my 3 different equations there for what's going on horizontally. I then do the same vertically. So y is, and in this question notice I was told g is 10, so I'm not taking it's 9.8, it's 10. So y double dot is negative 10, integrate it. I've got a constant, substitute in the initial conditions, find the constant. Now I have the vertical component of the speed. Integrate it again, I get this plus a constant, put in the initial conditions, find the constant. Therefore I now have an expression for the vertical component of the displacement. So going through that example is a good thing. So if we look at the acceleration as being expressed as negative gj, I can integrate that as a vector, so this is like doing both bits of the y and the x at the same time, and it gives me this new vector plus c, and then when I find what c is and substitute it in, I find that c is this particular vector, which means I can then rewrite as a new whole vector. And as I say, what we're really doing is you're doing the x and the y at the same time here, and it just makes it faster, and it's just as valid to simply take those 2 equations separately and then express them in vector form. You can then do similarly and integrate again, and then we have these final equations. So these are the general equations we've got for both situations if it's projected from an origin with an initial velocity as given there. Things to note that are often used in questions is things like the maximum height is when the j component is 0, of the velocity that is, and things like if the vector projectile returns to the same horizontal level as projection, the total distance is twice the horizontal distance, and so on. And things we're looking for there is that the speed would end up being the same going up as down, but with the vector. So things like the vertical speed would be 0 at the top of that point here. Things like the displacement would be the same here, this is vertically, as it would over here at B in terms of the vertical displacement, but the horizontal displacement will tell me what the whole range is, and so on. So all the same things apply as usually apply with projectiles. So this is example 3 continued. So we looked at the first part of it where we used it to find those 6 time equations, and it'd be a good idea to then go through the rest of this example and talk through that, showing this example like the vertical component of the velocity is 0 and what that means and so on. Here's an example that I've put together that you might find useful to use. So just to go through the basic idea of the projectile in terms of a vector equation, And then just doing some basic things, finding the things you usually find with projectiles. How long does it take to get to the ground again, the speed with which it hits the ground, the maximum height, the initial speed, and so on. So let's look at the first one first of all. So when does it hit the ground again? So it's at ground level when the j component of r is 0, and I've already got r, so I'm just putting that 500t minus 5t squared equal to 0. Solve that, and I find that it reached the ground again at t is 100. I've then got, for part B, what speed does the projectile hit the ground with? Notice speed was asked for, not velocity, so we're not that fussed about the angle, we're just worried about the size of it. So if I've now got this r dot t, which I've got by differentiating this, that means that we've got this particular equation here that I can use, and I'm finding it at a particular time t is 100 because I just worked out on the last slide that it reaches the ground again when t is 100. So what is the speed at that time? We substitute in, we find the magnitude of that vector, and we're there. For part C, when does it reach its maximum height? And in fact, I want to know what is the maximum height, I think was the original question. So it reaches the maximum height when the j component of the speed is 0. Well, we just found the speed vector, so we're putting the j part of that, 500 minus 10t equal to 0. So t is 50, so the maximum height happens when t is 50. Perhaps we could have even have got that from the fact we knew the total time was 100 and we knew that it was a parabola and there's symmetry. So we're putting that into R, and we know it's the j component of r is the height, so we're looking at the j component of r when t is 50. We make the substitution and we have our answer. And finally, an initial speed when t is 0, obviously, so we're finding the speed vector for when t is 0. We substitute in and we find the magnitude of that. Example 4 is quite important because it's got a nicely set up problem there where we've got two possible angles we start with, and I've also, as you'll see in a minute, picked out some questions for the exercise that goes through that, because that's quite a common thing. So make sure you read through this, make sure you understand the diagram, get your students to draw the diagram, the two possible ways in which it could hit F, what could be going on there. There's one example there, what would the other one look like? And work through that with them. It's a good one. Here are some good questions from exercise 10A that give you a nice variety of things. So starting off with some basics of finding the things like I just went through in the example, when does it return to ground, what's the horizontal distance, and so on for questions 4 and 5. Question 6 is more of a show that at the end in terms of showing that the initial velocity is at a particular angle, so that just puts an extra layer on there. And then questions 9, 10 and 11 are all ones where perhaps we've got different variables in there. So we're trying to do some different show that's. We're given an angle in terms of an inverse tan, and here we're asked to find the initial speed of the projectile, and in part 13 find where these whether they collide, and if so when they collide, with two different projectiles going on. There's an extension question 17 here that is a really nice lead-in to 10B if your class and you are feeling up to it. I thought I'd go through that here for you. So we've got a particle projected from the floor of a horizontal tunnel that's 2 meters high, and it just touches the ceiling of this tunnel. So in other words, we know that the maximum height of that projectile is 2 meters. Prove the horizontal range is a particular thing. So we start off and set up my initial condition equations. Excuse my handwriting on this. Laptop was playing up a little bit. There it is, looks a bit nicer there. So we start off and we're going to create our 6 equations. So we start off with the fact that we've got the acceleration in the horizontal direction is 0. We integrate, we substitute in the initial condition, we get the second equation. We do the same again and we get the third equation. We do the same in the horizontal direction. Y double dot is negative g. We integrate and we get our 5th equation, and we integrate again, substitute in initial conditions, we get our 6th equation. So they're the standard ones, but we should show that every time. And that's a really important point to make to the students, and the same will be the case in 10B. You've got to show where it comes from every time. So now we start to play around with the algebra we've got. So when y is 2, we've got that the vertical velocity is 0 because that is the maximum point. So that means that I've got this particular equation, the equation for y dot is 0, which gives me that I could replace t with v sine alpha over g if I feel moved to do so. I might write down what the vertical, the range is, because that's what I'm trying to find out eventually, isn't it? I'm trying to find out what is the horizontal range. So I could find out x at that particular point is up to there. I've substituted in the t, but that isn't giving me what I want. And of course, I also want to double that eventually. So let's go back and look at y. So y is my vertical range, and I know that it's equal to 2, and I've found what t is, so I can substitute this t value into my original expression for y. If I do that, I find that I've now got an expression for sine alpha, which is going to be useful in terms of this x that I'm wanting to find here. So I could express sine alpha in terms of g and v, and hence, of course, using the Pythagorean identity, I could also express cos alpha in terms of g and v. So going back then, when y is 0, I've got that this expression is 0, that was the expression for y, and so t times this is 0, which means either t is 0, well that's happening at the start, isn't it, or t is this particular value. This particular value can have the sine alpha substituted into it, as I did just now, and actually there's a much simpler way of writing it. Now that's looking a bit more hopeful because I've got a 4 in it, and I have a 4 in my answer. So I'm saying that when it gets back to the original starting point, I have now an expression for t at that point. So going back, I had this idea of x, and I've got this idea now of, I've got an expression for sine alpha, I've got an expression for cos alpha. It's all looking as though I might be able to do something with this now. So when t is this particular value, what is x? X is vt cos alpha. So I've got v, I just put as v, I've got now an expression for t at that time, and I've got an expression that I worked out previously, that I could use for cos alpha. And now it just becomes a question of rearranging that. If I bring these things underneath the square root sign here, then my v squareds cancel, and I've got what I was asked for. So that's nice because you're talking in general terms, and in general terms is exactly what 10b starts to go into. So the equation of path is what we're looking at here, this idea that we could find an expression, a Cartesian equation of the path. There's a strong link here with parametric equations, and as I say, if we've done some harder examples in 10a, there isn't a lot more to do here, but an important point to make to the students is do not memorise the box on page 489. They need to do it each time, and we always need to show all our workings, so the derivation of where I'm getting these things from. So this is the general case, and I'd focus on this rather than the box. So the box, I don't think I even give it here, is an orange box on that page after this, the general case, which gives you the formula for this. But seeing as you can't use the formula for this, there seems very little point in doing that. The reason the box is there and the reason the formula is there is because sometimes in a question it gives you that formula. So it's showing you it so you might recognise it and go, oh, okay, yes, that's what I do with it, but they shouldn't be learning it. So working through this general case with the students would be a very good idea to show them again where those 6 equations come from. Arguably, the more you do it, the more familiar they'll be with just following that process. And in this case, playing around with it a little bit. Remember, we can use things like the Pythagorean identity and so on. I would then go through example 5 to reiterate that general case. So the workings of that goes through the general case, this one again, but in a slightly different context, and goes through that. So example 5 would be an important one then to go through. And after that you could go straight into doing some questions from the example, because you've done a lot of the work already in exercise 10a, especially if you've done that number 17 with them. Then I'd go straight into this. I'd be getting them to do these questions here, which gives you a nice range. This one here particularly is a little bit like what you've just done in the example 5. And doing questions 9 and 9 and 11. 11 is an extension question, so you might want to give them some support through that question depending on how the class is going and how you feel they are ability-wise. And finally then, I would actually at this point, because they've done an awful lot of questions by this point, and some of them are quite complex, I'd then save that chapter review for revision at a later date coming up to an assessment, or perhaps even just prior to the trials.